Hi, my name's Jason Patrick, and welcome to this free technical training on submarine power cable current rating calculations. First, I'm going to speak about the fundamentals of current rating calculations. I'll give you an overview of submarine cable design. I'll talk about the bonding arrangement for offshore cable, submarine cable systems. Then I'll show you how to model submarine power cables. I'll talk about accurate armor loss calculations. Then I will discuss the critical sections for an offshore wind farm installation, including the landfall. I'll talk about dynamic ratings, then the J-tube sections and the seabed sections. I'll give you an overview of the 2K criterion. Then I will give a live software demo where I'll demonstrate how to calculate current rating calculations, how to perform current rating calculations for submarine installations and J-tube installations. Finally, I will draw some conclusions and provide some recommendations. The software used for this training course and for the modeling is ELEK Cable HV software. As you can see from the icons at the top of the screen, this software has a great deal of capabilities. It is fully validated and complies with IEC 60287. It's suitable for any AC voltage cables or HVDC cables. It can perform current rating calculations for custom cables, including complex submarine type cables, under your specific installation conditions. For a free trial of the software, please visit elek.com. IEC 60287 is the main series of standards that are used for analytical current rating calculations. This standard is widely adopted in the industry and allows us to produce consistent and comparable results. It's regarded as reasonably accurate and reliable and is adapted for common cable types, modern cable types, and installation methods. It's needed to be extended quite a bit to deal with power cables, and we've done that in our software. There are 9 parts to the standard, and it's really quite complicated and ambiguous in parts to implement. Submarine power cables design. Typically, the conductors of these cables, 3-core submarine cables, are copper. For some projects, there's a mix of copper and aluminium for certain sections. For very deep water applications, aluminium conductors are almost always used because they are lighter, easier to install and retrieve if necessary. XLPE is the first choice for the installation for these types of AC or DC cables. There are dry type designs and wet design cables. The dry type cables or dry design cables have a welded metal sheath, either aluminium or lead. You can see in the picture shown here is a 3-core submarine AC cable with a welded lead sheath around each core. The red arrow points to the lead sheath. Lead is the typical first choice for the metal sheath for dry design cables. Dry design cables are typically used for the export cables for wind farm installations, and the wet design cables, which are a cheaper design, are used for the inter-array cables. These cables are armored cables. Typically, a galvanized steel wire armor is used. However, steel armors are preferred since they are non-magnetic and produce lower losses. Stainless steel grade 316 is recommended. However, it's very, very expensive. The outer serving of these cables is interesting and is typically a polypropylene yarn. The bonding arrangement for offshore HV submarine cables is always solidly bonded. This is for practical reasons. Now, solidly bonding the armor and the sheaths results in relatively high circulating currents, not so high as single core cables because these submarine cables are predominantly 3-core cables with which produce lower circulating currents in the armor and the sheaths. Here is an example of a 30 kV submarine cable where the current rating is 920 amps at 90 degrees Celsius. That's the conductor temperature. And as a result of solidly bonding the armor and the sheath circulating current is around 85 amperes, which is relatively significant and results in additional heating inside the cable and derating of the cable. Let's talk about modeling of submarine power cables. These cables are quite complicated. There are lots of layers inside of them. Now, to model them, we need a manufacturer data sheet with all of this construction data. We need to know the material types and their dimensions and their electrical and thermal properties. The challenges include incomplete information in these data sheets, the fact that we often need to combine cable layers, and important properties such as lay length factors are not included often in these data sheets. And even if we go back to the manufacturer, very often we're not able to obtain some of these important information that's required for current rating calculations. With the incomplete or missing information, very often we need to perform back calculations. So that means that if we know the dimensions of a certain layer, but we don't know the dimensions of another, then we can back calculate based on the thicknesses, etc., that we do know. And it's a very good idea to, when you're setting up the model, to do some simple validation. Often these manufacturer data sheets will include some standard calculated current ratings or an indication of the current rating for certain limited conditions. Now, if you model the cable according to the data sheet as best as possible, and then you do some simple calculations in software to try and match the data sheet indicated current ratings, if you're in the ballpark, then you can you can say that the model is reliable, the cable model is reliable and can be used for further studies. Very often these cables, because they're complex, they require modeling of custom layers, and it can be a challenge to match the materials according to the data sheet. But it's very possible to have a good, reliable cable model, and that's an important starting point for the current rating calculations. I'll just run this. No, I'm not able to run this brief video in how I'm presenting today, but this is, you can see the cable data sheet in front of our cable model editor. Perhaps I'll do a demonstration of the cable model editor at the end of the presentation. Let's talk quickly about the thermal resistance of the fillers. You can see that we have these profile sections. These are plastic shape profiles, reinforcement that hold the three cores of these submarine cables together. Often there are voids within these. Now, if the cable is above the ground or not underwater, then these voids would be air-filled. However, when the submarine cable is installed underwater, then these voids are filled with water. For the purpose of the current rating modeling, these voids are ignored, and they're assumed to have the same thermal resistance or resistivity as the main material. There is also a jacket typically around the sheath or around each core. You can see the arrow on the left that is pointing to the thin jacket around the lead sheath on these cores, and that also needs to be accounted for in the modeling. Magnetic armor loss calculations are important because these three-core submarine cables are armored. Now, typically, according to the IEC 60287 standard, when you are accounting for the additional losses caused by magnetic armor wires in these cables, there is a simple multiplying factor of 1.5. Now you can see this multiplying factor of 1.5 in two main equations. The first equation is for the conductor AC resistance. So actually the magnetic armor around the cable increases the main conductor AC resistance according to the IEC by a factor of approximately 1.5. That's a direct multiplier with the skin and the proximity effect factors. The equation at the bottom shows this 1.5 multiplying factor for around the cable that also affects the sheath circulating currents. So the armor actually increases the circulating currents within the lead sheath of the three-core cable. Now, this is a relatively simple way of dealing with magnetic armor and the losses caused by the armor. But it's widely regarded nowadays by the industry that it's conservative, and there is a better way of doing it. So CIGRE Technical Brochure 908 came about in 2023, relatively recently. That was brought about by concerns particularly coming from cable manufacturers working in the wind industry. They were concerned that these multiplying factors provided by the IEC 60287 standard were too conservative and resulting in derating of their cables, unnecessary derating of their cables for submarine and wind farm applications. So a working group was put together, and they did a lot of analysis using the finite element method, etc., a lot of modeling to check or confirm or discredit this the IEC standard method. And they came up with a better method. The result was that the implications of their method were that actually conductor and sheath losses were increased. It was found that the 1.5 multiplying factor for the sheath losses caused by the armor was actually not conservative enough. However, the armor loss factors or the armor losses were being significantly overestimated using the IEC method. And the overall result is that current rating improvements came into effect using that method, and you can expect around a 10% increase in the current rating of your three-core armored cables using this technical brochure method. Our software has implemented this method, and I'll show you a demonstration of that here. So on the left-hand side, we've got a simple installation. We've got a three-core 30 kV submarine array cable with 3 by 630 square mil copper conductors with galvanized steel wire armor. On the left-hand side, if you were to bury that cable at 1 meter below the ground, and use the IEC 60287 current rating standard, it would result in a current rating of 830 amps. Now, if you perform the same calculations but using the CIGRE Technical Brochure 908 for accurate armor loss calculations, the current rating would be increased by almost 10% to 920 amps. The table at the bottom of this slide gives a breakdown of the losses within the cable. So you can see that conductor losses are slightly increased, or almost 20%. Now that's also because the conductor is carrying a higher current. And then you have sheath losses. Remember I said that there is an increase in using TB908 of around 30% in this case. Remember I said that the technical brochure found that actually sheath losses were being underestimated as caused by the armor with this 1.5 multiplying factor. So there's an overall increase in sheath losses. However, if you look at the armor loss, the difference between the IEC method and the TB method, there is almost an 80% reduction in armor loss according to this updated calculation. And the overall result is almost a 10% increase in the current carrying capacity of this submarine power cable. Let's look at a typical installation and the critical sections with regards to cable ampacity. Starting from the most onerous or the worst section, resulting in the highest derating of cables, would probably be the landfall. That's point number one there. And the next highest derating or the most onerous section would be the J tubes. That's where the cables rise up from the seabed onto the infrastructure above the water level, be that an offshore substation or an offshore wind turbine. And then there's the seabed, which also needs to be considered. The cables are typically buried in the seabed. Let's talk about landfall section design. So typically these sections are either an open cut trench or horizontally directionally drilled with ducts. So the cables are typically installed in quite relatively large ducts. If HDD is difficult with certain soil types, so you would the preference would be to use open cut trench. Typically, the burial depth for these cables at the landfall would be between 10 and 15 meters. That's the maximum burial depth, resulting in the lowest current rating, most likely. The thermal resistivity of the soil at the landfall is higher than at the seabed. That's due to the different soil structures, but also because at the landfall, the soils are not saturated with water. The ducts may be filled with a pumpable grout, and it's recommended that if that's done, that these grouts do not become solid over time, or else it will be impossible to retrieve the cable if necessary. Soil drying out is a real concern at the landfall above the water table level. That's a critical section where soil can dry out, resulting in higher cable temperatures and could be a significant bottleneck in for the wind farm installation in terms of current ratings. We recommend a duct size of between 1.5 to 2.5 times the cable outer diameter. Now, an important point here also about the design is that, remember I said that these submarine cable installations, the bonding arrangement for these cables is always solid bonding of the sheath and armor. Now, that can result in high circulating currents, derating the cable significantly. And that's also a problem, even more so at the landfall, which is typically the main bottleneck for the wind farm in terms of current rating. So what's been done in industry, and there's a reference to a paper on this slide, where actually single point bonding has been used at the landfall itself. And that has resulted in a significant increase in the current capacity of the cables at the landfall. So that is a measure that you can take. Let's talk about the modeling at the landfall sections. So obviously the depth of burial and the soil resistivity are two main factors that have a significant impact on the current capacity of the cables at the landfall. So we need to have a good idea about those values. And typically the deeper the cable, the lower the current rating. So we need to consider the deepest burial, the deepest depth of the landfall cables, and to use that in the modeling. We should also consider whether the ducts are filled with water, or they are filled with air, or they are solidly filled with a grout or a pumpable material. We can do that in the modeling. And finally, at the bottom left hand of the slide, for very deep burial depths, we should also calculate the soil temperature rather than use conservative values such as 20 degrees or 15 degrees as an assumption. We can use ambient air temperature and variations, meteorological data to better predict and to calculate soil temperatures at large depths. Also, on the right-hand side, we should consider soil drying out at depths above the water table. We need to consider sections where the soil could dry out. That would typically be at shallower depths, not necessarily at the deepest depths of the cables at the landfall. And in the bottom right-hand corner, you'll see some finite element method modeling. If you have a very complex landfall installation where you have a large pipe, and there are ducts, cables in ducts pulled into this pipe, then you will not be able to use the standard IEC 60287 methods. You'll need to use a form of FEM, and our software can do that sort of calculation. Dynamic ratings of export cables at the landfall is a very important consideration. Because the export cables at the landfall are typically the bottleneck, we should use the actual wind load generation rather than assuming that these cables will be running at full load rating continuously when they won't be. Typically, these sort of installations or a wind farm is running at between 50 to 70% of its full load rating when you look at that over time. Now, because the export cables at the landfall are deeply buried, we can take advantage of long thermal time constants for these sections, and we can use the actual load profile from the wind farm. You can see an example of that in the top right hand corner of the slide. We should use years of data, years of wind data, and we use particular conversion methods to convert that into a worst case what's called a multi-step profile. And from there, we can actually calculate a less conservative dynamic rating using the IEC standards to assess the worst case load event during the cable life, which is typically less or lower than assuming full load rating, continuous load rating. In a real world example, shown here on the slide, the rating of a deeply buried 220 kV export cable increased by 8.4% by using this method. Let's talk about the J-tube sections design. J-tubes, as you can see from the image shown here, they transport the cable from the seabed up onto the platform, the wind turbine platform or offshore substation platform, where they are attached. The cable is attached to the platform. They are open-ended at both ends, obviously, and the J tube, there is a bend in the J tube towards the seabed. That bend depends on the height of the tube from the seabed and the angle, the desired angle. But typically, these angles range between 15 to 45 degrees. The inner diameter of the J-tube, to avoid any difficulty in pulling the cables up through the J-tube, should be at least 2.5 times the outer diameter of the cable that you're pulling in. And the bending radius should not be less than 20 times the cable outer diameter, but you should consult the manufacturer for the minimum bending radius. And these tubes can be made of multiple sections with vertical air gaps to facilitate air circulation, and there's some recommendation there. Let's talk about the modeling. So there are in terms of the thermal modeling, there are two main sections to the J-tube. There's the section below the water and there's the section above the water. The section of where the cable is inside the J-tube above the sea level is the most onerous section, resulting in the lowest current ratings or the highest temperatures. Now, there is no method provided by the IEC standards for calculating the current ratings of cables within J-tubes at present. There is a new working group that's been formed, and there is expected to be a future IEC standard on this topic. However, at ELEK Software, we've developed an analytical approach based on heat transfer principles to deal with this situation, and it can calculate the current rating of the airfield section and consider solar radiation exposure as well as wind speed, which also affect the current rating, and the dimensions of the J-tube itself, including the diameter of the J-tube and also the length of the J-tube. These have an impact on the current rating and are considered in our thermal model. So some of the main factors that affect the ampacity of cables within the J-tubes. Remember, it's the airfield section, which is the critical section. So let's look at the top right-hand corner plot. As the length of the airfield section increases, the current rating of the cables within the J-tube will decrease. There is a major impact caused by the airfield section length. The bottom right-hand corner, you'll see the effects of solar radiation exposure. Now, because the J-tubes are vertical, it doesn't need to be assumed that all of the surface areas of these J-tube, the outer surface of the J-tube, will not be fully exposed at all times to solar radiation. A typical assumed area is 50% of the outer surface area. However, there's also a value of 32% mentioned there, which comes from a relatively old paper, but they give some good reasoning. So it's not 100%. However, so solar radiation has a moderate impact on the current rating. If you shade the J tube compared to direct solar radiation, you could expect perhaps around a 15% reduction in the current carrying capacity of the cables within the J tube, which is relatively significant. And then wind speed, the bottom left-hand corner, that has a less of an effect. The worst case would be to assume still air around the J tube. But if you were to assume a continuous wind speed 2, 3, 4 meters per second, you could see a minor, it's actually not a decrease in the current rating of the cables in the J tube. Let's now talk about the design of the seabed sections. So typically the cables in the seabed are directly buried. These cables are buried at between 1 to 4 meters with a usual or typical burial depth of 2 meters. The shore areas are difficult regions where it's often not practical to use these ploughing devices to pull the cables. So you may see the use of concrete mattresses or cable covers. At J-tube entries, rock dumping is often adopted. This is reasonably controversial. Thermal resistivity tests are performed along the cable routes, along the entire cable route. So samples are taken of the soil and measurements are performed in a laboratory of the thermal resistivity of the soil in the seabed where the cables are going to be installed. Typical soil thermal resistivity for the seabed is relatively quite low, between 0.4s to 0.8, but you could see values of up to 1.4, which is regarded as exceptionally high, but that would be a seabed where there is a high organic content in the material. And the typical soil temperatures are also quite low, usually between 5 and 15 degrees Celsius. However, these seabed temperatures are highly variable and you should consider several years of data. In the table in the bottom right-hand corner, you'll see some thermal resistivity values for water-saturated soils, which you can consider for your designs. Let's consider the current rating of cables that are installed under the water or in the seabed. So starting on the left, you'll look at this plot. Starting on the left-hand side, you'll see the current rating for the same cable when it's completely in water. It's higher than when the cable is partially buried in the seabed or completely buried in the seabed as we move from left to right in this plot. So the current rating for cable that is completely buried in water is, in this case, is around 1250 amps. Now, as we start to bury the cable within the seabed, the current rating reduces until it's So it reduces to below 1100 amps as we bury it in the seabed. Now, the difference here when cables are installed in water or partially buried is that we are considering convection, water convection. So cables that are completely in water, we are considering natural and forced convection. So forced convection means the flow of the water. When they're partially buried in the seabed, we only consider natural convection. And when the cables are fully buried in the soil, so if you go to the very right-hand side, the last point at 0.2 meters, you'll see the current rating of the cable has completely dropped off when we're using the IEC direct buried or buried installation calculation, and the current rating has reduced to below 850 amps compared to 1250 when the cable was installed completely in water. You can see along the bottom of the slide here the different thermal models that we're using. Not the one on the bottom right hand corner, that's something different. That's where I'm making a point that should we consider marine growth for ampacity calculations, perhaps we'll do that in the future, but it's an interesting consideration. Now, it should be pointed out that the models for cables completely in water or partially buried are not available within the IEC standards, and those have been developed by ELEK software. Let's look at the current rating of cables that are completely in the water, and an application of this in the top left hand of the slide is for dynamic cable systems. These are a new sort of invention that are coming about with the advent of these floating offshore wind farms and substations. The dynamic cables will no longer be buried within the seabed, they'll be floating. And so we can take advantage of the fact that the current rating of cables that are completely in water is much greater than cables that are buried in the seabed, which is a significant advantage. So therefore, if we look at certain factors that are affecting cables that are installed in water, starting with the bottom left-hand corner plot, we've got water temperature. That has a significant impact on the current rating. So as starting from left to right, as water temperature increases, current rating will significantly decrease more or less linearly in a linear fashion. Now, looking in the top right-hand corner, you can see water velocity. This has a low to moderate effect. So if you consider that the water is still, or if it's moving, this will impact the current rating slightly, not so much. So if we consider 2-3 meters per second at most of flow, you can see the current rating will increase. And the bottom right-hand corner, to even less of an effect, is the water salinity. So for fresh water, the current rating is slightly lower, and for highly saline water bodies, the current rating is actually increased. The 2K criterion is a quite restrictive criteria that in power cables that are installed in environmentally sensitive areas, and it's a criteria that is adopted within Germany and sometimes in other parts of the world. Now, that criteria states that the temperature rise caused by submarine power cables should not cause an increase in the ambient soil temperature of more than 2 degrees, so 2 degrees above the natural ambient temperature, within 200 to 300 millimeters of the seabed surface. That environmentally, that's regarded as a critical section. Now you can see an example here in the plots. So we've got a 320 kV HVDC submarine cable system buried at 1.5 meters below the seabed surface. Now, if we were to operate the cable system at its full capacity, the current rating would be 2035 amperes, but that results in temperature rises within that critical seabed depth of above 2 degrees, so it wouldn't comply with the 2K criterion. So to comply with the 2K criterion, on the right-hand side, you'll see that we needed to reduce the current carrying capacity of the system to 1,579 amperes in order to comply with the 2K criterion, which is almost 500 amps reduction, which is quite restrictive and limiting for the cable system. Right now, I'm going to perform some demonstrations, live demonstrations of the current rating calculations for submarine cables for cables installed in seawater and below the seabed and partially buried cables, as well as cables within J-tube. Okay, so let me give a brief demonstration of the software modeling. Here I am showing you the submarine installation method, but other useful installation methods for submarine cable installations could be in air, could be directly buried, buried in backfill with ducts, soil dry out, also even tunnels, then J-tubes and submarine installations in the seabed or the seawater, and of course FEM, the finite element method. So here I've got two cable circuits buried in the seabed, two different cable types. First thing I'll do is I'll show you the cable model. So this is the 3-core submarine cable. On the left-hand side, you'll see these are the cable layers used in the model. You've got the conductor screen, standard layers such as the insulation, etc. But you've also got custom layers such as these tapes. General settings on the right-hand side. So here where we set the phases, the number of cores, the voltage level, the frequency, the lay length factor of the cores for a 3-core cable. And then we go through, what we do is we go through each of these layers and we specify the properties. So for the conductor, the diameter, the conductor size, the range, class, etc., the material. We can set custom materials, DC resistance calculations, conductor types, whether it's millican, etc. We can set custom material properties if we want, but those values typically come from our database, which makes it much easier. Insulation screen, the sheath. Around each core, it's a non-corrugated lead sheath. We can specify custom sheaths. We can specify or calculate the DC resistance. We've got the filler, more custom. We've got custom water blocking tapes. We've got the Armour bedding. We've got the Armour itself, steel white Armour. We need to specify the number of wires, the thickness of the wires, the lay lengths of the wires. The properties are automatically propagated for the wires, or else you can customize those. And then finally, the jacket of the cable, polypropylene yarn, and you can see the outer diameter of this cable model. So that's the submarine cable model that's being used. We can also custom temperature limits for the cable to operate at 90 degrees, same as the insulation, or we can customize that. Otherwise, we can set a loaded current. Say we want this cable circuit to run at 500 amperes, for example. I'm just going to set it back to 90 degrees, and then we can also set the bonding arrangement and the daily load factor. Okay, so I've got two cable types in memory that I can use for the studies. Here in the submarine installation, I can move the circuits around any way I like. I can have any number of circuits in any arrangement. The mutual heating, all the calculations are performed live. Again, you can see the soil temperature plot. Now, let's look at the rating of these cables. So 890 amps when it's buried in the seabed. I can move it into the water, and you'll see a significant increase due to the different thermal model, actually of all circuits, because this cable that's now in the water is not mutually heating the other circuits due to the high levels of convection happening in the water. I can embed the cable within the seabed, and the current rating will be adjusted. I can make an accurate depth of cover for the cable, say 50%. And like I said, the current ratings are automatically updated. I can adjust things like the thermal resistivity of the seabed soil, increase that, decrease ambient temperature, change water velocity for cables in the water, adjust the salinity, etc. And of course, the positions and the current ratings are updated live. All of the current rating results are on the right. Here is a summary result, including the current rating of the circuits, or the complete results, including the bonding, the electrical losses, loss factors, electrical properties, sheath standing voltage, sheath circulating currents, also sequence impedances and thermal resistances, cable temperatures, and a summary of cable construction. These results can be exported as a comprehensive PDF report or an Excel report. Let's briefly look at the J-tube installation method. So I've got the environmental properties here, so the air temperature above the sea level, and the wind speed, water temperature, water velocity, water type, etc. I can adjust all these. The length of the section of the J tube in the air, the length below the water. This also has an effect in our thermal model. The duct dimensions, I can select an appropriate duct and select a duct material. In this case, that should probably be a metallic conduit. Exposure to solar radiation. So I can specify an exposure, an area of exposure, and I can also specify the solar radiation intensity. However, I can also calculate the intensity. I can simply enter a location. This has Google Maps integration, and I can move the pin to wherever the project is located and perform accurate solar radiation intensity calculations for a particular period, over years or months or weeks, at a location at a particular elevation as well. And I can export these results and use those in the calculation of the current rating for cables installed in the J-tube. That concludes the brief demonstration of the software for submarine cable calculation. Okay, so let me draw some conclusions and provide some recommendations. IEC 60287 is used for accurate ampacity calculations in combination with certain CIGRE technical brochures already mentioned. Submarine cable construction is complicated. We need a cable data sheet to model the cables. There can be missing information. These cables, because of their complicated construction, require extensions to the IEC standard in terms of their modeling. They typically have a jacket around each core and they are armored. And very often with the cable manufacturer data sheets, there is missing information. Solid sheath bonding is used for submarine cable systems. We saw that at the Landfall, being the most critical section of an offshore wind farm. We could also adopt single point bonding. J-tubes are another critical thermal bottleneck, and typically the underwater sections have a higher rating but may become significantly constrained by the 2K criterion. As recommendations, we recommend to use dynamic rating for deeply buried export cables at the Landfall by considering actual predicted wind load data. Use CIGRE Technical Version 908 for accurate 3-core armor loss calculations that will increase ratings by approximately 10%, and use the finite element method for complicated installations, including multiple cable circuits inside pipes. Thank you very much for attending this free live technical training. If you would like to try ELEK Cable HV software for free, please visit elek.com. Thank you again, and we'll see you next time.